another book yesterday on
Mhm.
NMR, and I
Mhm.
got some stuff down. I probably have a good question. So, the chemical shift on the spectrum,
Yep.
is that just because of the shielding, the electron shielding? Is like that what determines it?
That is one factor. Yes. And for you, we don't even have to understand exactly the nature of what causes shielding and deshielding. Our approach is the practical approach. Use that information about what the number is and what it can mean, just based on the table. Because there are other factors, like when you get to the end of reading the chapter in our book, you'll see that benzene has a unique characteristic.
Right, I read aromatic compounds like I
Mhm.
saw like the hydrogens or something like
Well, the
go in
pi
circles.
electrons are going to go in a circle in response to a magnetic field. Just like when you put magnets close to each other, they either snap together, or if the
Right.
poles aren't lined up, they're going to repel, right? Well, what happens is all the benzenes align so that the circling electrons cause their own magnetic field that causes a stabilization, and the opposite resonance where the circles going the other way is much higher in energy, because there's why I mean that's big disadvantage to get that unfavorable rotation direction, right? But anyway, that's a lot of talk. All we have to know is benzene shows up at 7.2, and
Right, I noticed like
it's a
the
unique
aromatic
number.
compounds
Yeah,
are like further down.
it's a blessing, because almost every pharmaceutical out there has benzene in it, and benzene has that unique signature 7.2 on the NMR, so you can immediately spot the benzene part of the molecule just by looking at that area of the spectrum and say, yep, we got benzene, got a 7.2 peak here.
One thing I had trouble kind of understanding, like I know the like the peaks, like there's different like peaks within the one peak, and
Yeah, the
that's due to
multiplicity.
coupling.
Yes.
That's
Well,
uh
how far they are apart from each other has to do with coupling, and we won't even get into that at all. Like,
okay.
but we do have to know the patterns, which are predicted by Pascal's triangle, right?
Is that what we refer to as the coupling constant? Is like like I
That's
read about that. It says is proportional to the distance between the tops of the peaks and the multiplet.
Yeah, but we're not even going to worry about I'm going to switch screens here for a second,
Okay.
because what you brought up is a point that I don't get into at the introductory level, and I'm just figuring out how to share screens for the first time apparently. Here we are. So if we have two triplets, and my pen's recharged. It's over here. So we got a triplet that looks like this. Height 1, height 2, height 1, compared to another triplet. And they're both triplets, which means the H's that contributed to this have two neighbors, because 2 plus 1 is 3, which is called triplet, right? Same
Okay.
story here. And that's as far as we go. But in your reading, you were saying, oh, the distance between this little peak inside the triplet and the next one, that's called the coupling constant, right?
J, I
J.
believe.
And this one has a bigger coupling constant. And for us, we don't even care.
Okay.
We don't get into that. But it is useful information, because if you see a peak like this, and then you see another peak, let's say a triplet, where the ratio, quartet, sorry, I said triplet, quartet, the ratio is 1 to 3 to 3 to 1. If I drew a little better, it probably look closer to this. Then if you had to answer the question, what hydrogens are these hydrogens coupled to, and you only have these two choices, you're going to say this one.
Why is that?
The effect of the coupling constant of these H's on this peak is the same as the effect of the coupling constant of these H's on this peak. These are too close to each other. If it was coupled to another, it clearly is, so you'd have another peak somewhere in the molecule, maybe a doublet. I don't know. It doesn't matter what the peak is for this purpose of this discussion. And you see the doublet looks like doublet looks like this. Oh, I'm trying. I should put my straight drawing tool on. And you had to guess, is this coupled to one of those or this? You'd say, well, the distance between these two is the same as the distance between these two. That was my intention anyway. So these are
Oh,
coupled
okay.
together, and the distance between this and this is the same as the distance between this and this. That was my intention.
So those two are coupled
They're
together as
coupled
well.
together. And yeah, that's a nuance that we don't even get to that level. I'm just trying to make the distances match up a little better. Look at me. I did it. What about over here? Did I do pretty good there? Not bad for a guy that can't draw. There you go. So yeah, and yeah, oh, I never saved. And I'm just gonna save it. Yeah, you're seeing all my file names here. Ooh, dangerous. 242.
So when you apply, say, okay, you have like a substance and you put it in the, I'm assuming the NMR machine is simply just
right.
a strong magnetic field. They push different frequencies of light through and
Oh
then
no, not light. Not light. It's a different
radio wave.
form of radio. Yeah.
Okay. So they push different frequencies of radio waves, correct?
Mhm, yep. And that makes
then it plots the absorption.
It makes two spins that used to be the same energy have different energies because they interact with that big electromagnet that you
Right.
turned on.
They
Yes.
were all pointing in different directions, and then when they're in between the magnet, they go between alpha and the beta spin, just between
You're
those.
even naming them alpha and beta now. Yeah. Clockwise, counterclockwise. Yeah.
Is
Yeah,
that
they
the same
alternate.
thing?
Yeah. Yeah. We don't even
Okay,
even use those Greek. We have enough Greek in this course, right? But
Yeah.
that's yet another example, and you read about it.
Okay, yeah. Honestly, I think it's it's easier to me to understand they alpha and beta, but I mean, I can see like if you say it's counterclockwise, that would be,
Right.
well, I know when put in between when you're putting the substance in between a strong applied magnetic field, it aligns them one way or the other. So with the magnetic field and misaligned with it, right?
Right. So the ones that get are with the right spin that are with the magnetic field get stabilized, and the ones that are against the magnetic field get destabilized. Yes.
And then that's the action of going into resonance when they flip.
Now you're going to apply your own specific radio frequency for that particular hydrogen in question. If you give it the right frequency exactly, you cause it to get excited to that misaligned energy state. And then it stays up there for just a bit because it's not happy up there, right? It's unstable. And then it relaxes and reverses its spin back to the lower energy state. And then it absorbs more of that energy that's still there. You kept your little radio frequency on. It still absorbs it again and goes back up, and it relaxes down to the more stable state and absorbs the energy again. And this is the resonance we're talking about, isn't it? We're going up
So it
and
goes
down,
back
up
and
and
forth.
down. Yeah.
Okay, up and down, rather.
Doesn't matter. Yeah, however you want to say it, right? Just twist your head sideways, and now it's back and forth.
So that happens after being within the magnetic field, just say
Yes,
like over
nothing
a little period of
happens
time.
until you turn on that electromagnet, the big electromagnet. Yeah.
Okay.
Mm-hmm.
Do you have a test, an exam problem with like the actual like spectrum on it we can like analyze?
The versions of those questions we do have. It doesn't have the spectrum, but it has the data that is the spectrum. It gives you the ppms and the patterns and the number of H's. And have you tried those yet?
No, honestly, I haven't. I haven't looked at the exam.
Here's what I want you to do. I want you to try like the introductory ones found in the textbook first. And if you're stuck on those, then we should do one of those. Now, if you can get past a couple of those, I want to get to the one where you're starting to have troubles, and that's where we can take advantage of our Q&A the best.
Right. Okay.
So
I should be able to pull something up really quick.
And let's see. I'll just write some comments while you're looking. Coupling constants, not covered in this course.
So we don't have to worry about coupling at all
No,
as a concept? Okay,
no, you have to know how to draw the patterns. So how to
right.
draw a proper triplet and how to draw a proper quartet, but don't worry about the spacing between the peaks in those patterns, is what I'm trying to say.
Okay.
We'll just say
Okay. I found the sample one in the textbook. It's like the table